My name is Hazim Gaber, and today we're going to start with part 1 of the Structured Cable Systems course. We're going to be looking at cable types, and we'll see in a minute that there's specifically, we're going to be covering principles of transmission. In metal. And you're going to find out why this is such an important topic in a few minutes. So, the most common type of electrical conductor. How do we want to know? We have, a source and a recipient. So, we're generating data here and we're sending data here, and we need a medium to carry the data. That's a pretty simple idea. And the way we carry the data is with a metal wire. When we have a bunch of wires together, because let's say the recipient, the source needs to send data, great. Now the recipient needs to send its own data, so we need a second wire. And if we were to combine these two wires with a jacket, we'd have a cable. This whole thing is a cable. Now, obviously, if you have any background in IT or cabling, you know, for example, that Cat 6 contains 8 wires. We're getting a little bit ahead. So let's think about what kind of metal should we use to make a wire. And we have a few choices. We have copper, which is the most common. And then we have what we call copper clad. So some people will say copper clad steel or copper clad aluminum. And basically, what we're doing is copper is very expensive. So if we make the entire wire out of solid copper, it might cost us, $1 per foot. But if we take an aluminum wire and we just make the skin of the wire copper. So now this is aluminum and this is copper. And aluminum is much cheaper. We could probably make this for, say, 20 cents a foot. And we take the best of both worlds. So we have copper, so we get the performance of the copper, but we also have the cost of the aluminum. Now, obviously, I would never install copper clad aluminum ever, but some people do. And in a lot of electrical installations, people use pure aluminum for carrying high voltage power, and they're allowed to. Now, many architects or many electrical engineers will say, will prohibit the use of aluminum. It's legal under the building code, but some engineers don't like it. And one of the disadvantages of using aluminum for electrical conductors is that you have to use a thicker wire. So, for example, if you have a 6-gauge copper wire, to use the same aluminum wire, you have to use a 4-gauge aluminum. Note that a smaller gauge number means a thicker wire. We also have we call high strength alloys. So there's applications where we need the conductivity of the copper, but we need the strength of another type of metal. So in that case, we get a big pot and we heat it up and we add some copper and we add some other metal and we melt them together, and then we make an alloy wire. So this wire will be intermingled with the two metals, and it will have the conductivity of the copper, but the strength of the other metal. So the best conductor is actually not copper. Well, gold is a very good conductor, and you'll see in some Cat 6 jacks they will be gold plated. One of the advantages of gold as well is it doesn't corrode, so it has a much higher lifetime, but obviously it's much more expensive. So now, if we look at copper, we look at conductivity. Conductivity is how is the rate at which the electrons move through the wire. If we take copper and set it at 100%, so let's say, for sake of example, conductivity is 100 miles per hour. Then, if we had some other metal like aluminum, we could say aluminum moves at 80 miles per hour, so it's 80% conductivity. I just made these up, but we can compare the conductivity of another metal, say, and then we can look at the cost benefit analysis of the cost versus conductivity. And we can see if a lower performance, or we could say if a higher performance justifies the additional cost. So we've got, for example, and there are other reasons. So say I have a pole and I have another pole and I put my wire And this wire, let's say it weighs, 1 kilogram per foot. Physics lesson. So if this is 1,000 feet, then this cable or this wire is 1,000 feet times 1 kilo per foot. And I know I'm combining metric and linear, but let's say this weighs 1,000 kilos. Then what if the breaking strength of the copper is only 500 kilos? Then this cable is going to break in half. Or even if it doesn't break in half, the force of gravity is going to start to pull on this cable and it's going to sag, which is acceptable, and then it's going to stretch. So eventually it will break in half. So we can add some steel to it. Obviously, we're going to add the steel before we install the cable. And one of the things we can do, going back to the previous slide, is we put a steel core and a copper jacket. So the conduction happens in the copper layer on the skin, and the strength comes from the steel. And now we have a steel cable that won't sag or bend. Won't sag or break, but it's got the conductivity of the copper. We can also add other types of metals. And they're about 85% conductivity. But we can reduce the weight of the wire. Now, of course, I said, so some examples are, for example, zirconium or cadmium. So we're combining zirconium with the copper, and now we have a lighter wire. There may be areas where we want to have a lighter wire, like on an airplane or space shuttle. And then we also have aluminum, which I said before. So aluminum is only 60% conductivity. And it doesn't rust. And it's lighter. And it's cheaper. But may not be permitted by drawings or engineers. It's legal to use, but you may have a contract, or you may have a drawing, or you may have a specification that says no aluminum. Then you can't use aluminum. So if we are to compare aluminum has the worst conductivity. So we say best conductivity, worst. You get copper, and then copper clad, and then steel core or alloys, and then aluminum. And then the strength, the best strength to the worst. We have the steel, and then we have the copper clad, then we have copper, and then we have aluminum. Well, I should say this is an alloy. Now the next thing we're going to look at is what I call solid versus stranded. So we've taken our copper wire and we've peeled the jacket, and you can see with the solid one we've got one piece, and with the stranded one we've got multiple wires. So in a data cable, what we call a permanent link, we're going to have a solid conductor, and a patch cable going to have stranded. A lot of wires though, a lot of electrical wire will be stranded too. So solid is cheaper, and it's easier to terminate because if you have you just have one connection to make here, whereas here you have to try to get all of these strands together. You may have to solder the ends. And of course it performs better. These ones are obviously more expensive and more difficult to terminate. Poor performance. I wouldn't say poor, but like not as well. But they are flexible, which is why we use them in patch cables. If you bend a solid conductor too many times, it'll have fatigue. So if I have a piece of metal, solid piece of metal, and I bend it in half, it'll start to get weaker at the bend. And if I bend it back, we'll end up with like a little divot. And then eventually it'll fail. So if we're using a cable in an area where it's going to bend often, we should consider a stranded cable. If we're using a cable in an area where it's just going to be run once, we should consider a solid cable. A lot of electrical cable, though, is stranded because when you're talking about trying to work a really thick cable through a conduit, it's a little bit more difficult to do with a solid cable. And then you can also look at composite conductors. So a composite conductor is one that does not, or that contains something other than metal. So, interestingly, graphite and silicon, which are not metals, are conductors. And we can use those to our advantage. One of the reasons we might want to look at a composite is it's cheaper than metal. It doesn't expand under heat. So whereas a piece of metal, if we heated it up, it might expand 10% per 100 degrees or whatever. A composite might only expand 1%. And that makes it much, much better to be used in a device that requires precision. Because we may not have much room in a USB drive or a watch or a cell phone. Trying to make a cell phone small and light, we might think about using a composite, especially if a cell phone's susceptible to heating up. And the other thing is when metal heats up and cools down, also starts to fatigue, wear out quickly. So we're trying to avoid that. One of the problems, though, with composites is they are brittle. So whereas metal, it can bend fairly easily, a piece of graphite, you think of like a pencil lead, if you hit it, it's gonna break. It's not gonna bend. Whereas if you hit a piece of copper wire, it'll bend. So it needs protection. Also, hello. And quality control can be difficult. So right now, not recommended by Hazim. Now, I should have mentioned this earlier. But we measure wire thickness by gauge. And the reason is we start off by getting a big pot and we put our metal into it. And then our metal heats up until it's molten. And we pull it through a mold and we make a wire out of it that's pretty thick. And then we try to pull this wire through another mold that's a little bit smaller. And then a little bit smaller. And then a little bit smaller. And then a little bit smaller. And so we said we start numbering these wires. So this is, say, gauge 1, or I should say 1 gauge. 2 gauge, 3, 4, 5, 6, etc. And goes on forever. Because the more pulling we need, the higher the gauge. So the lower the number, the thicker the wire. And everybody does this. And we can come up with a table that shows us what all the gauges mean as far as thickness goes. So we'll cover more on this later. But basically, if you want, typically data cable will be 23, 22, or 23, or 24 gauge. And there's a huge table that covers the gauge and then the diameter. And then we've also got, you can get these tables with other details like weight per meter and length per kilo and resistance, which is important if you have a specialty application. In our case, we're not really going to cover much more than the data and some electrical, but in general, this is left up to the electrical code. So if I were to say smallest gauge is actually 0, and it's 8.25 millimeters diameter. If we look at, say, 6 gauge, it's about 4 millimeters. 25 gauge is 0.455 millimeters. And obviously this goes on for quite a while. Then we also have insulation. And the purpose of insulation, going back, if I have a cable with multiple wires, I need, if these were all made of pure copper, they would all, we would not be able to keep the signals separate. They will all bleed into each other. So I have to cover each copper wire with a layer of insulation. and that prevents electricity from moving between them. And we also don't want people, if this was a high voltage power line, we would also not want people to get electrocuted. So we're protecting conductors from each other, and we're protecting the conductors from the environment. And so in the data cable, the type of insulation affects the performance of the data cable. So there's two things. One of them is what we call it a dielectric constant. And the other one is known as the dissipation factor. So the lower these are, the better we perform. And what are they? Well, dielectric, you'll see it, the label is K, and it's basically a dimensionless. I'm getting too much into the physics here, but it's a ratio of the wire permittivity. Or i.e., how basically does it's kind of hard to explain. Shouldn't say that, but does this material allow electrons to pass out from the material into the air? And the less likely, the more it hangs on to its electrons, I should rephrase this. So a high dielectric constant means that the material likes to hang on to the electrons, which we don't want. We want the material to flow. So what I should say is that the insulation can hold some of these electrons that are passing through the wire. And we don't want an insulation that allows electrons to leave the wire, and we don't want an insulation that hangs on to the electrons and stores energy. So if we do have an insulation with a high constant, we're going to have poor performance of the wire because a lot of the traffic, a lot of the electricity is going to be absorbed by the insulation. And we're trying to avoid that. The same with the dissipation factor. We don't want the insulation to allow electricity to leak out. Then we'll have poor performance. So there's a number of types of insulation. And we'll get into this in more detail later, but at the best insulation is FEP, and the worst is one of the worst is PVC, platinum rated. So a platinum rated cable will perform poorly compared to a non-platinum rated cable because of the high dielectric constant in the platinum cable. So 3.6. Depends on what you buy though. But you've got non-platinum PVC, which is 3.4. And then you've got basically polyethylene, which is also bad. It's around 2.3. I mean, sorry, polyethylene, which is one of the best, but we might not use polyethylene if we need to have a platinum rated application. So if you want to think about it, I'll just summarize. The dielectric constant, air, is 1.0, and the idea is we're comparing the capacitance or ability to hold electrons. So lower is better because we can think of air as not being able to hold any electrons. So we want our insulation to not hold electrons. It's like you have a garden hose and you have water flowing through the hose. You don't want the hose material to absorb the water. You want all the water to go out. You also don't want you don't want it to leak. And that's what we call a dissipation factor. So imagine not like your dog chewed through the hose, but imagine there were like micropores throughout the hose and little droplets of water were sweating out of the hose. Eventually, the hose was long enough, and none of the water would come out the other end. So we also don't want that. And as i.e., you can think of it as power loss. Is the insulation absorbing some of the electrical energy? The more that it is, so obviously we want this to be as low as possible as well. There's a couple other things. One of them we call it dielectric strength, which is a maximum voltage insulation can tolerate. And that's where we're going to stop.